So, we will continue with our discussion today on tension leg platforms. Now, there are certain distinctness about this which are different from your semi-submersibles. The major point of departure is in the tension in the cables. So, this is your pile foundation. So, this is called foundation template. So, these are actually pile. Then you can have your the riser from your wellhead assembly. So, this is called a well template. Now, normally you will find the blowout preventer stack at the bottom, but in some cases you may find at the top. So, BOP stack is normally you will find in case of floating platforms, it is positioned at the wellhead. Now, here the point that is to be discussed is templates, TLPs different from semi-submersibles. Now, their structure is also slightly different. Now, TLP structure you will find mostly closed array pontoons. Now, this type of structure is not amenable for transit. So, this is one major point of difference. Another point is invariably in semi-submersibles, the configuration that I have given you, you just have a look. Then semi-submersibles you will find normally there nowadays 2 pontoons with 3 columns on each pontoon. So, this is the normal configuration. So, this is the present scenario. Now, here actually TLPs bracings are minimal. The underwater structure that is to be designed, bracings are minimal or sometimes they are absent also or totally absent. So, this type of structure is more suitable for TLP's design, that is should be more motion friendly, restrictive in motion. What is with heave? With zero heave. So, this is where you go for a TLP. Now, if you find that you can do with some heave, then it is better to go for semi-submersible. So, these moorings, TLP moorings are essentially on tethers. So, tether is actually the main mooring connection with the seabed. Now, tethers also give what? You provide the righting moment against capsize. So, this is the main function of the tether. One is to this tether function, you provide righting moment and also reduce motions. Now, here the tether arrangement is of primary importance. How do you arrange the tethers? Now, based on your tether arrangement, the other configurations. So, tether arrangement you have to do to reduce motions. So, this is normally done, this is the main advantage of tethers. Now, here a lot of configurations have come up. The one that I have drawn is your closed array pontoon. So, here actually pontoons will be on the all the four sides. Now, these are your braces, you can do away with these braces, but one thing you should note that columns are very large in diameter. Compared with pontoons. So, that means the major part of the stability is coming from the columns. So, columns give your damage stability. Columns provide damage stability. So, whenever you are thinking about stability, then and pontoons are essentially, pontoons give structural strength. So, your major strength member is your pontoon and damage stability is coming from the columns. So, subdivision, you have to subdivide columns. Column subdivision is important. Now, obviously, pontoons have also to be subdivided. So, there should be pontoon subdivision as well. Now, these two have enough free space. Now, why this is coming? You find in TLP you have a lot of free space or abundant space. This is because large amount of buoyancy has to be provided. So, basically you have to have enough buoyancy to support your tendon tension and the weight of the platform and of the payload, etc. So, all these things we have to have sufficient free space and also riser configuration, column spacing, depends on riser spacings. So, this you have to configure. Now, next coming to the decks. Now columns actually most TLPs have 4 columns. Hutton TLP, that was in 1984, Hutton TLP had 6, but the present scenario you will find 4 columns. This is your present. So, present structural configuration is this. So, the columns actually will provide damage stability, and what else it is providing? Columns provide support to deck at 4 corners. Now, so when you design the deck, so you will find that it rests, the deck has to rest on 4 points. So, this is your deck. So, it will be resting on your columns out here. Say another column out here, etc. So, these are your columns actually provide support to your deck at 4 points, and in between, since you are doing away with the truss members, then the deck should have ample rigidity. Now, if you increase the column spacing, your deck span also is going to increase. So, that also you cannot go on increasing to a large extent. So, here you have to, deck has to mate with columns for installation. So, this is one of the major points that you should remember. Their column spacing is to be decided on length and breadth of deck, column spacing. Now, coming to the deck, you have to decide, first you decide whether this is going to be an open deck or in naval architecture this is called hull type deck, like ship hulls. Now, this open deck has certain advantages. Disadvantages are, advantages you write. What is the major advantage is self ventilated. You do not have to bother about ventilation, and this is very important for oil platforms. So, if you have entrapped gases which can ignite, so those are actually driven away if you have an open deck. Now, disadvantage is no buoyancy. In case of capsize. That is another major disadvantage. Another advantage is crew can work in enclosed environment. Now, actually in TLPs your damage stability calculation is very important because of these reasons. Crew can work in enclosed space. Now, if you have an enclosed deck, so that means you have to have good mechanical ventilation inside, because you have to drive out inflammable gases. The hull type is essentially the reverse of this. Basically, they do because of greater enclosed volume. And so, this is the major advantage. This is coming because of damage stability. Now, remember that damage stability calculation in case of TLP is very important, because at this region, at your water line, you will find lot of impact, etc., wave impact, and then barge impact etc. will come. So, this is the major region which has to be thought of from accidental damage. This is flooding zone. So, flooding zone is on the columns. So, deck, coming to this, so deck is, you decide whether you go for an open deck or a hull type deck. Now, open deck is a truss. Now, these two types, deck is normally, you will find sometimes the deck is fabricated in a separate shipyard altogether. And the hull is also fabricated in a separate place and two joined at site. Because you see, the deck design will depend on your the process facilities, the oil processing facility, the drilling, whatever equipments you have on all these things. So, deck normally fabricated in a separate shipyard and hull is fabricated in a separate shipyard. Now, here the problem comes in matching deck and hull. Matching deck and hull. So, this is the major problem, and installation. So, this is the major problem. So, you have to do your buoyancy and stability calculations. Buoyancy and stability calculations to be done during installation. So, there is, for naval architecture, this is the job. First, you have to do all these buoyancy and stability conditions during what? During tow, then during installation, and last one is in the operation phase. So, these are actually different drafts. Now, you have to calculate these drafts during tow, installation and the operating mode when it is drilling or recovering oil. So, drafts are different. So, you have to provide your hydrostatics and GZ curve. So, this is your, the buoyancy and stability part is over. Now, next is coming the other part, that is the TLP, is the hydrodynamic load. So, first you do your preliminary design. This I have already talked, I think, last class. Your preliminary design, so what is your main objective in preliminary design? Here you fix up vessel size. So, that is your main depth, draft, all these parameters are to be fixed up here. So, here you have to do a lot of iterations, primarily with your hydrostatic stability, because that is the major factor, and the items that I told you is weights and CGs. So, these are constantly changed in order to have favorable hydrostatics, damage stability, and later on you will find motions. So, these have to be calculated. Now, next you calculate wave forces, then wind, then current. Now, from these three forces you find vessel offset. Vessel offset and set down. So, this is why this is very important. So, this actually you will find this leads to increase in tendon tension. Now, how much you can accommodate the increase depends on your tendon configuration. So, basically you have to decide the strength of cables, number of cables and breaking strength. So, these have to be decided. So, tendon tension is very important in case of TLPs. Now, after this all these calculations, that is why calculation of wave, wind and current forces very important. Now, this you gather from oceanographic data. And then you calculate motions. So, motions in, you have already restricted heave from heave comes under this tendon tension. Now, what about this motion? Surge, sway, yaw. Now, these you have to find out from rows. Rows are basically your transfer function. So, you have to do a lot of, now you will find that this is also related to your, all these are related to cable spread. Cable spread. So, this is another important parameter which decides on column spacing. Remember, your TLP is basically centered around these motion characteristics. The buoyancy and stability is not that important, but these motions have to be minimized. And the last one is global strength. Now, here actually the strength is not as your ship strength. Now, here you have to find out from TLP riding crest or trough. So, here you calculate wave, mainly your acceleration, wave acceleration force. So, mostly you will find that inertia force is predominant. Inertia force is predominant in this sort of structure. Now, these have to be calculated. So, you will find a lot of hydrodynamic calculations you have to do besides the structural configuration. So, that ends your preliminary design. Now, coming to the hydrodynamics. So, you will find the various configurations of your teeth, the one that I have drawn. Now, you can extend your TLP, the pontoons. So, pontoon configuration can also be like this. So, these are called extended leg TLPs. Now, basic reason I told you because you want to have a spread on the you increase your tendon spread. Now, later on you will find if you increase tendon spread, then you can reduce the pitch motions and also your vessel offset. So, this is called your extended leg TLP. Other form you can also have, instead of having this one column, if you want to have a smaller TLP, then you can support the deck. Now, I told you the previous one that I have talked about, you will find the deck is resting on 4 columns, but here you can see that the deck is having a substantial overhang. Now, here at the middle you can have, say, this is a, these are the columns. Now, column, and each column you can protrude the pontoon. I can't draw the shape properly. So, this is a star shaped platform. Your pontoons will in this configuration it will come. This is called a star shaped. Now, here you can see that all these columns are more or less not very much distant apart, they are giving support to the deck. Now, here you will find deck has large overhang. Pontoons star shaped. So, why you are going for this type of complicated shape when you can do with the simple shape? Now, at the end of these pontoons you can attach your tethers. So, this is another arrangement. So, your design actually you have to figure around, I am telling you, first is you decide on this type of, either on this type or on this type based on your riser spacings. You cannot neglect your riser dimension. So, this type of closed columns, if your riser spacings allow, then you go for that. So, this is another type. So, this is called a star shaped arrangement. Now, basic thing is he has done is, here you can see the columns are much more slender than this type of 4 column arrangement. So, he has reduced the wave load. So, main design will be centered around, now you see large diameter columns, they have a inherent weakness, that is increases wave load. That is, your diffraction load is going to increase. I suppose you have studied wave refraction, diffraction and all these problems. Now, here also, but large diameter columns gives good deck support. Now, you have to optimize between these two. Now, you can see here the deck is having an overhang, and in between you have number of columns, slender columns. So, this is more wave transparent. the wave loading is another. From the hydrodynamic calculations, you will find a lot of calculations you have to do. You have to calculate the drag forces that are coming onto the hull by their second order forces, first order forces. Then I told you about wave run up and all these things. So, the TLP motions are actually governed by the wave mechanics. So, this part you have to decide whether you are going for this type of arrangement or this type of arrangement. Now, you can see the reduction in the pitch and offset you have done by increasing the tether spacing, and you have not increased the column spacing. Column spacings you have limited. Now, here actually if you the tendons if you attach on the end columns, then if you increase the column spacing, then obviously your tendon spacing is going to increase. So, that is one of the major drawbacks. And next you have to think about, now this sort of deck you have to first you think about deck supports in all the two arrangements. Now, find deck area, and if you cannot accommodate all the equipments, then you go for number of decks. So, here actually this deck is called, and if you go offshore they are called top sides. So, that is why the top sides are actually fabricated in a different shipyard altogether. So, top side layout and number. Top side, rather you simply say top side layout. So, top side layout is very important in case of TLPs. Also in case of semi-submersible, same thing. Any offshore activity or offshore platform you go, first thing they will tell you to design top sides. So, here actually this major point is coming because of support to your deck. Now, coming to the mechanics part, you will find that your weight, say the common TLP that we are having. So, the deck is resting on say in the columns, corner columns. So, this is the most prevalent design, very easy. The other types of design you have to, they are non-conventional design and they are for a particular environment. So, here you draw the free body diagram. Now, the weight will be acting somewhere, let us support the weight is coming from downwards and the major buoyancy force is coming somewhere here. Hold on. Now, next your tendon tension is acting downwards. So, this is tendon tension. So, what we find is that total buoyancy is equals to, this is your weight plus delta W. So, delta W is your variable weight. And this W naught they call light ship. This is your total weight and this W is your buoyancy. So, your buoyancy has to support, what is the buoyancy equation? Rho g So, that is going to support what? Your weight, or sometimes you call that ship weight, plus what is TR? So, that is the, now this actually you can call W naught. So, this is your buoyancy. This is your weight. TR is what? TR is riser tension. Now, actually your TLP has to support both your cable tension and riser tension. Riser is also kept under tension, similar to your cables. So, NT is number of cables, and this is tension in each cable. So, this is your basic equation, the hydrostatic equation you have to formulate. From this you calculate displacement. And get draft. So, this is a hydrostatic equation. Now, any change in this displacement, say delta W, this is equal to how much? Your rho g water plane area multiplied by change in draft. So, change in displacement is equals to the water plane area into change in draft. So, displacement change, because these things water plane area you cannot change, this is given by columns, from columns. So, this is fixed and draft can be changed. So, displacement change is related to draft. Now, you see there is another parameter which is called set down. So, this is your TLP in the vertical mode, in the normal mode. Now, suppose it is struck by a wave and there is a set down, what will happen? Say this is your TLP when there was no wave force. So, everything is, your weight is coming down, buoyancy is going up, tendon tension is coming, this is your free body diagram. Now, the TLP is displaced. So, there is a offset. Now, as a result of this offset, what has happened? There is a set down. So, you calculate vessel set down. So, this is your new configuration. Your original position was somewhere here. Now, what has happened here is this is the direction of a horizontal force, but your cable is anchored to the seabed. So, you will get another downward force. Now, here also there will be the cable tension will come like this. Now, you find out how much is the offset. You calculate this angle phi. So, you will find vessel offset created by, so your offset is, this is your offset or x, offset x. Now, here I have not shown, but actually your deck will also be in this region, it will come down. So, this is called a set down delta z, x is called offset. Your TLP set down has occurred. Now, this is one of the reason in TLPs actually you go for a larger air gap rather than semi-submersible. In TLPs, because of this delta z, air gap is very crucial. Air gap requirement crucial because of set down. In semi-submersible, you do not have a set down. Semi-submersible will simply go in the surge, or you can, there enough cables are there, chain cables are there to take care of them. But here you do not have so much of chain cable, so it will set down is going to happen. So, air gap is better to maintain large air gap. But if you have large air gap, there will be another problem, rise of G. So, everywhere you have to strike a compromise between all these parameters. Now, the vessel offset you will find this creates set down. And as a result of this, what will happen? Increase of cable tension. So, this is another point in TLPs that will come because of set down you are having increase of cable tension. Now, offset is created by summation of these three forces. Wave force plus current plus what? Force coming from wind. Wind, wave and current. So, from this, actually these three forces calculate offset. And after you calculate offset, you calculate set down. This is your delta z or delta z, and after this you calculate increase in cable tension. Now, this increase in cable tension should not be so high that it leads to cable snap. because of offset. So, if you have a very large offset, then your cables cannot accommodate that, so it will snap. So, this is you will find in your the next equations, you have to calculate what is the increase in the offset. Now, so change in displacement we have found out. Now, you find out the cable tension. So, tension in each cable is, so the tension that we have worked out is rho g delta minus, there are two forces, minus the weight and riser tension, isn't it? So, this is cable tension and this is your riser tension. You simply divide this by number of cables. So, this is your equation. Now, in change in cable tension you write delta T. So, what is your delta T? This you can find out. Is okay. So, this is your water plane area and delta D is change in draft. NT is the number of cables. Followed? Now, you find out this. Now, if you calculate set down, now set down is actually your delta Z. So, delta Z is your delta D or change in draft. So, now you calculate this. See, this is your now you calculate the angle phi. So, your length of cable will remain the same LT. Now, offset is x, followed, and this angle is phi. Now, from this diagram can you calculate set down? So, sin phi is how much? X over L by T. Now, if you take the, now this tan phi is equal to f x over n t t t. Now, this n t t t is always, you remember that this is always a vertical force. So, that means this n t t t is acting in this direction. However, this is your displacement, you should not mix up this, because in our buoyancy equation, so we have n t t t counteracting your weight and buoyancy, all these are normal. So, from this we can get this tan phi. Now, set down is how much? You just look at this diagram. Set down is given by delta Z. So, this arm is, do not mix up with this force equation, you just calculate the length. So, how much is that length? This length is how much? Say first you calculate this A, B, C, you forget about delta Z. So, AC squared is equals to LT square minus x square, followed. So, AC is equals to how much? You write like this, you bring that LT out. So, this is LT square into 1 minus x over LT, this is square, is it right? So, this is your LT into root over 1 minus x over LT square. So, now what is your set down? So, set down delta z, this will be LT minus LT into root over 1 minus x over LT square. So, this if you simplify, this comes to LT into, this is 1 minus so this is your set down. Now, this set down will transport into increase in tension. So, delta T, you find out delta Z from this, this will be rho G A W multiplied by delta Z divided by LT. So, this is your increase in cable tension. As a result of set down delta Z. So, this actually is very important, delta T. So, this should not increase to such an extent that it goes beyond the breaking strength of the cable. Otherwise, you can pay out. If this is increasing the tension stress, tensile stress, you keep on paying out the cable. But if you pay out this cable, you increase the length of the cable, then what will happen? Your riser is going to increase the length of the riser also. Now, that also is very risky. After a certain increase, the riser cannot accommodate that increase in the length of the riser. So, your riser snap will occur. So, TLP actually you have to be very, very careful about these two aspects. One is riser snap and tether snap. So, these two things will occur because of offset, TLP offset. So, TLP offset is normally you have to limit this. Now, the present day TLPs can accommodate, TLPs have been fabricated to accommodate as much as say 79 feet offset. 79 feet offset is no joke, whereas in your jacket platform, jacket can only give say 3 feet offset. So, remember, if you go on board a TLP, 79 feet going this way, that way. So, the next day you will say, you pray to God, you will get out of the TLP. Anyway, so that we will continue with our discussion.